going to wrap up with some advanced topics. We won't go too deep, but we give you a flavor and then we will conclude. And I will present this together with who will present a few slides on regression calibration. So this is the table of contents. There's not an awful lot of stuff here. Okay, an alternative view of calibration. So, so far we really talk about calibration as aiming to get as close as possible to the base optimal classifier. But that's not the only possible view of calibration, and it is, in a sense, limiting us to viewing calibration as somehow closely related to predictive accuracy. And so I will describe an alternative view of calibration which allows us to take into account different performance metrics, and I will illustrate this with F-score. And another thing that I will demonstrate from the cost-sensitive perspective is the use of Breyer curves. Telmo talked earlier about decomposing proper scoring rules into calibration loss and refinement loss, and we can actually visualize that with Breyer curves, which are a special kind of cost curves. So, as we've seen before, if you have misclassification costs, then really what you should consider is this cost parameter C, which is the cost of a false positive relative to the sum costs of a false positives and a false negative. And if your probabilities are well calibrated, then the optimal threshold on your probabilities is given by C. So if we use pi to denote the proportion of positives, then accuracy is, well, then the loss can be described in this formula here. So let's unpick that a little bit. There is the false positive rate, which somehow gives you the proportion of negatives that are misclassified, and you have 1 minus the true positive rate, which is the false negative rate, which is the proportion of negatives that are misclassified. If you multiply these with pi and 1 minus pi, then you basically are taking the class distribution into account, and then we use the costs. So we weigh one part of the formula with C and the other part of the formula with 1 minus C. And the factor 2 is there to make sure that even if you have C equals 1/2, which means you have equal misclassification costs, then you're essentially getting error rate back. Now, the Breyer curve plots this loss as a proportion, as a function of C against this value of C. So just recap: we have a well-calibrated classifier, we have a cost parameter, we set the threshold of our classifier equal to our cost parameter C, and then we vary C from 0 to 1, and we plot the loss. And this is called a Breyer curve. So why do we call this a Breyer curve? Well, it's very simple. We actually get a curve, the area under which is equal to the Breyer score. So let me show you the curve here. So I'll go forward one slide and then I'll go back to the other point. So on the left, we have 2 Breyer curves. So this is on an example with a known known distribution. So we actually know the true model here, but that doesn't really matter. We don't need to know that. And we trained the logistic classifier, that's the red curve, and we calibrated the logistic classifier that gives us the blue curve. And as you can see on the right, the reliability diagram, the red curve, there are some calibration issues, whereas the blue curve is perfectly calibrated. So the area under these curves is, of course, like the area under any curve. It is the expected value of the y-axis if your uniformly sampling over the x-axis, that gives us the Breyer score. So let me go back to the previous slide now. And so lower is better in this case because we have loss on the y-axis. But there is a lowest possible Breyer curve, which is the lower envelope of all possible curves that you can get by transforming the scores however you want. Okay, so a perfectly calibrated classifier has this lower envelope as the lowest possible Breyer curve. And by definition, the perfectly calibrated classifier has calibration loss 0, and therefore the area under that blue curve, which is the Breyer score of the perfectly calibrated classifier, and because the Breyer score decomposes into calibration loss and refinement loss, and calibration loss is 0, that blue curve visualizes the refinement loss. And so the difference between the blue curve and the red curve gives us the calibration loss of the uncalibrated model. So you see very clearly that you have for low values of C, for low probabilities, you have some calibration issues. Then in the middle bit, you have calibration issues, and then you have some calibration issues on the right bit as well. So that corresponds obviously with the reliability diagram, but the Breyer curves have the additional advantage that you now can make a link with Breyer score and with refinement loss and with calibration loss. So that's one tool that I've used quite a lot in my work to try to understand where exactly in which score intervals a model is poorly calibrated. So that's one connection with cost-sensitive classification. Now let's talk about a little bit more about the reinterpreting the output of a calibrated classifier. So as we know, a calibrated score, we can, so in my mind, I always convert quite easily between probabilities and things like likelihood ratios and odds. So if I have a probability P, that kind of corresponds to an odds or a ratio with those formulas. So if I have a probability P, then an odds can be obtained by R equals P divided by 1 minus P, and the reverse conversion is given by, if I have a ratio, then I take R divided by R plus 1, and I get the probability. So a calibrated score of P equals R divided by R plus 1 tells us that this instance's predicted class would not affect performance, so it would be on the decision boundary, but it wouldn't affect performance, whatever you predict for that instance, if indeed negatives are R times more important than positives. Okay, so obviously if P equals 1/2, R equals 1, and so a calibrated score of 1/2 tells us that this instance's predicted class doesn't affect performance if I don't have, if negatives and positives are equally important, but that also holds for different numbers. So a different way of saying this is that each calibrated score P has an associated weighted accuracy measure, which is written there. And if I was interested in that performance metric, then my instance P, my instance would be on the decision boundary. Okay, so the instance gets a calibrated score. The calibrated score goes as a weight into the accuracy measure. And then I can say, okay, if my classifier predicts 0.8 for my instance, then I know that this instance, the prediction for this instance wouldn't matter if negatives were 4 times as important as positives. Okay, so, but all of this hinges on using accuracy or weighted accuracy as a performance metric. What changes if we are interested in F-score rather than accuracy? So F-score is very popular in information retrieval, and typically F-score is used if true negatives don't add value. So Google doesn't get money for not returning web pages, for correctly not returning web pages to your query, not returning non-answers to your query. That doesn't make Google any money, so they want to take that out of the equation, which is why you would use F-score rather than accuracy. And so the question that I'm going to answer, oops. So look at the question at the bottom of this slide. Can we construct a calibration procedure that produces a weight for precision and recall such that the instance is on that weighted F-score decision boundary? So just to use the notation that people typically use F beta as a weighted harmonic mean of precision and recall. And for some obscure historical reason, there's actually a beta square there, and the weights are expressed in terms of beta square. Actually, it's much simpler if you convert those weights to that alternative weight in the 0-1 scale, D, and then you simply have D as the weight of precision, 1 minus D is the weight of recall, or if you prefer the right-hand formula, D is the weight of the false positives, and 1 minus D is the weight of the false negatives. So for F1, we have D equals 1/2. And so then we basically have the formula TP divided by TP plus the arithmetic mean of false positives and false negatives, or if you prefer 2 times TP divided by 2 times TP plus FP plus Fn. So all this is standard. So what I'm now going to demonstrate just with 2 figures is how to obtain scores from a classifier that will give us those weights D for which the instance is on the FD decision boundary. Okay, so we need to, so we're going to use precision recall curves, and on the left you see a precision recall curve, but there are lots of issues with these curves, so we've constructed a linearized version of that curve, which looks much more like a ROC curve. So essentially, we've taken that hyperbolic line in the middle, well, sort of not really in the middle, but in the bottom left of the left precision recall curve and kind of linearized everything and pulled that line up to the descending diagonal. And that gives us something that looks not completely, but quite similar to a ROC curve. And for example, it has a convex hull, and because it has a convex hull, we can use a procedure as essentially equivalent to isotonic regression to actually get calibrated scores out of that convex hull. And a result, an example is given on this slide. So on the left of this slide, you have the ROC curve, and you have calibrated scores derived from the convex hull, and you can actually see that because the scores are generally quite low, this tells me that the class distribution is biased towards the negatives. But what do these scores tell me? Well, for example, and let me just try and see if I can use annotation tools. Okay, let's see, sorry. I'll use the mouse, let me use the drawing tool actually here. So actually what these numbers tell me is that where would my standard decision boundary be? Well, there is a segment here that has score 0.75, and there is a segment here that has score 0.29. So actually my default decision boundary of 0.5 would get me to this point here. So this is the operating point that I would choose if I have equal misclassification costs, for example, and I use the prior that is in the training set, right? And this is This is the main advantage of having these calibrated scores, and I can do the same calculation for if I have different misclassification costs, for example. Now, on the right figure, I can do the same thing. So for example, I have now for each segment, and these are for each segment on the left of the convex hull, there is a segment on the right for the convex hull. But if I now ask myself the question, which point achieves best F1 score, then you've seen on the previous slide that a beta square of 1 corresponds to a D of 1/2. And the point that corresponds to 1/2 is here. So I now know immediately, without further calculation, without searching, without anything, that this point optimizes the F1 score among all these possible thresholds that I have here. But if I wanted to give more weight to recall, I would go further down, for instance, to this point here. If I wanted to give more weight to precision, then maybe I would go further down to that point, okay? So the thing that I have in mind here is that it is perfectly fine to have multiple scores coming out of your classifier. So your classifier could give 2 scores. One is a calibrated score for accuracy, as we have talked about for most of the afternoon. And the other, we could output a second number, which can't be derived from the first number. This is well known, but we can output a second number that says, well, if you wanted to use this classifier for optimizing F-score, then you need to use these numbers and not the accuracy calibrated numbers. So that's one thing that we had a NIPS 2015 paper about this, and you can read more about that there. Okay, so that's 2 topics with cost-sensitive classification. I'm now going to hand over to Hao for a few slides. Hao, do you want me to keep sharing my screen, and you can just tell me when to forward the slide, okay? So I'm going to the next slide.
Okay, so basically now we talk the question for regression. By regression, we mean, so in classification, you have a feature X, and your classifier gives you a probability over the target Y. So in the regression case, we assume that you are again from the same feature X, but your regression model gives a conditional mean and a conditional standard deviation, which effectively as a conditional Gaussian distribution over the X. So as in the multi-class case, you have multiple definitions of what we mean by calibrated multi-class regression. In regression, we face a similar situation. So here I'm introducing the first concept, which is quantile calibrated regression. Using a very simple case of temperature forecasting for a whole year. For instance, if you care about the median temperature, which for each day, they provide you a temperature, there is a probability of half that the actual temperature will be larger than this value, and half of the probability that the temperature will be lower than this value. And you can ask for this same median value for the whole year. Eventually, you observe the corresponding temperature for each day. If half of the observed value are actually larger than the predicted median, and half are smaller or equal than this predicted median, you can say this prediction is close to be quantile calibrated for the 0.5 quantile. And essentially, if you follow the math here, if we call a regression model is quantile calibrated, that is for any Taos quantile within 0 and 1, the condition that the actual target smaller or equal than the predicted quantile is always top. So that's one of the way to generalize the concept from binary classification to quantile regression. Could you go to the next slide, Peter? So here we can give an example for post hoc quantile calibration. So if you check the left figure, so the first dashed line is the predicted 0.9 quantile, but there are total 10 points, and you will realize out of 8 points are below the dashed top line, and 2 of them are above them. In the empirical case, this top dashed line should be the 0.8 quantile. So what you want to do is map the 0.9 quantile to the 0.8 quantile. And similarly, for the middle dashed line, while the uncalibrated one shows that this is the 0.75 quantile, is actually the 0.5 quantile. And similarly for the bottom line, although it's already being calibrated, which is from 0.5 to 0.5. So from this figure, from this two figure, now you check the middle figure, is that for the task of quantile calibration, we can use the same binary calibrator that effectively mapping from each uncalibrated quantity to the corresponding calibrated quantity. That is a way to achieve quantile calibration as proposed by Kull et al., which I cited in the previous slide. And if you could go to the next slide, Peter. And then, as in the case that we have true multi-class calibration in the classification case, we also have a similar concept for regression case, which we denoted as distribution calibrated regression. Although here we only consider in a simple regression case, this concept can actually be generalized to any conditional density estimator that your model provide a P of y given x. Although in regression case, you can think this P of y given x is modeled by a Gaussian distribution. So in this case, you assume that your model is a function f, maps the feature space into a space of probability density functions. And this model is defined as distribution calibrated if and only if for all the data point that receive density function s, the distribution of y is actually obeying this density function s. So we actually can prove a theorem as in the SML paper theorem 1, being distribution calibrated can be a sufficient but not necessary condition for being quantile calibrated. In the same manner, if you have true multi-class calibrated model, it is always class-wise calibrated and also always confidence calibrated, but not vice versa. So if you have distribution calibrated model, it's always quantile calibrated and not vice versa. And the next slide. So there are much more details, but given the limited time, we just give a quick example to illustrate the difference between distribution calibrated and quantile calibrated. Again, the right figure would be the same as the previous one. You only consider the dashed line that across all the feature space and represented the global quantile. However, in distribution calibration, you back to the individual case. For instance, for the rightmost 4 points, because they are on the same feature space, just on the same location within the feature space, they will receive the same estimation from the model. Therefore, you want this distribution, which is represented by the red dashed line, to be calibrated with this 4 point. That is the corresponding mean or standard deviation or any other non-parametric distributions. And similar for the cases. As you can see, distribution calibration can effectively achieve more detailed and locally calibration inside of the global quantile. Well, we have actually a nice method which based on Gaussian process again to achieve distribution calibration. But given the limited time, we would not introduce here. You are welcome to ask questions or refer the original paper afterward. Thanks.
Okay, thanks, Hao. So time to wrap up, and I promise we're nearly there. And I'll just wrap up with a few general comments. So I'm not going to summarize, but first of all, I labeled this slide the myth of the decision boundary, or I could equally have said decision boundary considered harmful. I think machine learners are obsessed with decision boundaries, and I think it's time to stop thinking of decision boundary and resist thinking in terms of decision boundary. This is like describing Mount Everest with a single contour line, which happens to be halfway up. To really characterize the whole mountain, you need many contour lines at different elevations. In fact, you need infinitely many ones. And it's similar in machine learning. The only case in which you really honestly should think about a fixed decision boundary is when your class prior that you used in training is meaningful, the misclassification costs, if they were there, that you use in training are meaningful and won't change. If your application is guaranteed to have those properties, then you can actually ignore most of what we said this afternoon, and just all you need to do is make sure that your decision boundary, your threshold is in the right position. So you could say, in that case, you only have to, in the two-class case, you only have to calibrate the threshold 0.5 on the posterior. But if you don't know this in advance, if things can change, if class distribution can change, if misclassification costs can change, then basically you want to calibrate all possible future decision boundaries in advance. And that's really what we've been talking about. So there isn't one decision boundaries. There are infinitely many of them, similar to Mount Everest having infinitely many contour lines at infinitely many elevations. So that's the first point I wanted to make. Secondly, and I've basically started by saying that calibration research predates machine learning and has been studied for 3/4 of a century. Okay, so there is a certain tendency in machine learning, because there, particularly in deep learning, deep networks have calibration issues. So it's great that these issues are being discussed, but it also has led to a certain amount of reinventing the wheel. So there is a venerable literature on proper scoring rules, on forecasting calibration. As I said, it's at least 1950, and so it's important that machine learners are not ignorant of this history. And maybe the NeurIPS paper that you're reading on calibration doesn't show that awareness of the history, but that means that you just have to dig a little bit deeper to go back to the origins. And related to that, there's a lot of recent proposals such as confidence calibration, temperature scaling, expected calibration error. They are all fine, but they should be interpreted in a context. They are not the only option. They may or may not be suitable for your particular application. So be aware of this wide scope of different ways of evaluation, different ways of calibration, and so on, and their properties. And finally, like many things in machine learning, calibration is an art as well as a science. So we've tried to teach you today both, in a sense. So we went back to first principles and tried to give the context, but also we tried to discuss lessons learned and things that we found out while we did this practically. And many of these practical questions don't have simple answers. It's like, how many faults in cross-validation, or how big should your training set be? There are possible answers to that question, but really most of these are empirical questions. So which calibration method, which evaluation metric, how many bins, what about validation set? And we've tried to address some of these questions, but more importantly, we've tried to give you the tools to actually navigate these questions and to explore them in your application. So this is also why we included the hands-on component, because we think that a lot of these things are exploratory questions. So you need to dig into your data, make your hands dirty, and that's why we made the notebooks and the Python code available. So, don't just run massive experiments and calculate single performance metrics, but really use the visualization tools to try and understand what's going on, what works, what doesn't work, and so on. So hopefully we've provided some useful introduction to the topic. We hopefully still, it is gone 3 minutes over time. We may still have a bit of time for questions. Otherwise, please reach out to us, and we'll be happy to engage in further discussion. Thank you.